Okay, great. So today we're going to be starting off, the first half of the lecture is on new material that won't be on the exam. It's important material and it's going to be a major focus on the final exam, but it won't be on this exam. The second half is going to be a review for the exam, which we will have on Monday of next week. It's going to be an hour and 15-minute long exam. So we will start out with the exam and then we'll have new material in that lecture afterwards. So we'll do both an exam and a lecture. I am going to assign, I need to make a note actually for myself so I remember this, homework for this week. But the homework this week is going to be relatively easy and it won't be due until the start of lab next time, because what the homework is start project 2. So I've looked over it. You guys should be able to get pretty far in project 2. I do expect you guys to get stuck and confused. But what I want is I want you to get to the point where you're stuck and confused by the time we show up to lab on Wednesday, so that we can hopefully do all of project 2 in just one lab week. It's not too difficult. I'll talk about it on Monday, I believe, after the exam. So if you've already tried doing it, then it'll make a lot more sense and you'll have some good questions. And then Wednesday, hopefully, will be just a lot of progress in signing it off. So let me take a note there. Okay. I went and got my vaccine today, so we'll see how my arm does. It's a little bit stiff, but we'll see how that goes. Okay, so what we're going to talk about today is called state machines. Now, we've been working up to state machines with combinational logic first, and then the sequential logic, right? Sequential logic is the flip-flops and the things that have memory. They're circuits that remember what they did before. So state machines are really just circuits that progress through a series of states that send out signals at appropriate times. Now, that sounds a little bit lofty or confusing or whatever, but we run into state machines all the time, and they're pretty easy to understand once we start doing examples. So, a common example of a state machine is a red light, a stoplight, really, right? Because it has, we could say, 3 states. It outputs red, yellow, or green light, depending on where it's supposed to be, right? And we have this tool to describe state machines. We actually have a couple, and that's what we'll talk about today, is the tools that we have to describe state machines. So the first way that we do it are state machine diagrams. And we always like to start off with like a default state. The state is often called idle because it's where we sit if we're not doing anything else. And it makes sense in the case of a stoplight to start with red, right? No one's going to get killed if everything is red. So we want to start off with red. Now, we'll get a little bit more into the how to draw proper state machines. So this one is a little bit incorrect in the final scheme of things, and you'll see why. Because right now, red is both the name of the state and its output, which usually we won't have that. But anyways, we start at red. And from red, we go to, well, green, right? So all we do for that is we draw an arrow, we draw a new state, and we're going to call this one green. Then we flow to a new state. This is really weird having only 4 students, but all right. And we'll call that yellow. After yellow, we go back to red. Now, state machines are sequential logic. That means they're clocked. So what that means is each time a clock happens, It's going to evaluate the conditions on should it stay in its state or not, right? And so this right now is what we would call an improper state machine because I only show the arrows to go to the next state. If we want it to be more proper, right, I draw an arrow that just, let's hang out in red, because that's what it's going to do most of the time, right? Because lights are slow. And even if we have a crazy slow clock on this, which we probably would, just because higher clock speeds mean, higher clock speeds mean more power, right? It makes more decisions per second. So in the case of red, if we have like a 1 hertz clock, right, 1 time per second, that's still many clocks each time it stays, or before it turns green ever, right? So we're going to have a couple of inputs, and I'm just going to kind of define these as we go along. And the first one I'm going to say is it needs to know if there's a car that wants to come through, right? So one of our inputs is going to just be C for car. And the car is detected. Well, that will go in this transition, car. We know that we will always stay red if there's no car. Now, that's not always true for all stoplights, right? Some of them cycle through on timers, but we're going to go with that. If there's no car, we will always stay in the red state. If we detect a car, that doesn't necessarily mean that we want to instantly go green, right? Because otherwise, we have the potential to the other way is green. We need to know. So our other input is, it's going to have, I'm going to call this NX for no cross. NX, no cross. So here we go. So we want to go to green if there's a car and there's no cross, right? Okay. Those are my two conditions. This is and, this is combinational logic, right? That this helps the sequential logic decide, is it okay to move in the next state? All right, well, we're in green, and let's just say we're gonna do the simplest way that is going to say, well, I'm gonna have a timer. I'm gonna stay green for some fixed amount of time. And if that timer happens and says that I want to flow, right? Yeah, we'll stick with just the timer, right? And then we'll say that, and this is going to be timer 1, and I'm going to have a timer 2 over here that is some different amount of time that I'm going to be yellow. So the only thing that happens is I sit in red, the car shows up, whatever sensor I have, it might be a light sensor, a weight sensor, or a radar, right? Whatever it is. And that C gets, and then it goes and checks, hey, is the other way green or not? Well, if it's not green, then I can bounce into our green. Our cars can go. We wait for an amount of time. That timer gets asserted. So what this means is here is there's this implicit not T1, right? And same thing for yellow, it hangs out if not T2. And that's all the state machine is, well, that's a state diagram. This is really the first planning phase that we would have of any type of state machine. Now, state machines exist in all sorts of electronics. They're kind of everywhere. And it doesn't really matter if you're programming in like VHDL or Verilog for a circuit, or in like C, C++, Java, etc. We use state machines in all of them. And you can imagine why that would be, right? There's really, if you go and pulled out your phone and you like look at, right, I have all those buttons. My state is I'm on the desktop. That's all. And it's just waiting for me to push one of these buttons to go to a different state. That's its idle state, is the desktop. And when I push a button, then it flows to open up, Twitter. And so these state machines are really kind of foundational for all of our programming because it's a good way to think. It's easy to draw. Now, obviously, the phone state machines get out of control, but you can have like hierarchical state machines, right? There can be a state machine inside of that state machine, right, and it goes down. Okay, so let's kind of abstract this a little bit so that I can simplify, because this one, actually, I'll complicate it before I go back and simplify. So this one has like an interesting issue because right now it doesn't have, the only outputs I've declared are the names of the state, right? And I haven't really given it a way to tell the other one, the other light, that it wants to change. So if both lights function like this is fine, right? Because both of them are just, if there's been no cars, say it's 2 o'clock in the morning, then what's going to happen in this case is they're both directions are just going to be red, right? Because they're both waiting for a car to show up, and neither of them is asserting this no cross signal, right? So they can both, either one of them can go green. It's just they're waiting. So that's not optimal, right? Because a more optimal state, situation, flow, transition would be one of them is green, whichever is the direction of higher flow of traffic, right? So we would probably want to add in like another state that has like a waiting state. And we'd probably add in some more logic that says, just stay green unless the other one requests it, right? So this is a little bit of an oversimplified state. That's okay. Now, I'm going to draw a state diagram that is fairly, well, basic. Okay, so there's going to be a couple of things that I want to show in this diagram first. So I'm only going to have one input, and I'm going to have one output, just for simplicity. And oftentimes you'll see we'll write start. Where do we enter this state machine? Okay, so we're going to enter at A, and each time a clock cycle hits, we're going to evaluate where do we go based on whatever in is. What is our input? So if our input is 0, I want to hang out in A. So I turn on the state machine, it starts up. If my input is A, and my output is going to be 1. Okay. That means if I'm a 1, I'm going to transition to B. And my output's going to be 0. And this is kind of an arbitrary selection, but I will. Great. Okay, so here's the state machine that I'm going to use to talk about for a little while. So the clock is going to be ticking along. And let's say our input, so here's clock, here's in, here's out. So our input, let's say it wants to start, I may actually need a few more clock cycles. Let's say it goes ahead and it starts out, and let's say our output is, we don't know yet, right? It's undefined, nothing has happened until our first clock. Then our input is going to start out at 0. Sorry, I'm trying to think of a useful, what the most useful pattern is. So let's say that's our input. Now, what is our output going to do? Well, it starts out, we don't know. We don't know what the output is because we haven't had an evaluation, right? We haven't had a rising edge of the clock yet. So after that, we get a rising edge of a clock and we see a 0. So what happens? Well, we hang out, and I'm actually going to write a new line that just says state so that we can talk about this. So in the first, our state is A, right? Well, if I see a 0, which I do, on the input of that first rising clock, I stay in state A, and my output is 1. And it stays 1 until the next rising edge of the clock. All right. Next up, I get a rising edge of a clock. It sees a 1. I'm in state A. I see a 1 as my input. That means I move to state B. And my output is now 0. Now I'm in B. I have a rising edge of a clock. What state do I go to? C. This input is 0. I go to C. And my output stays 0. So what else? This rising edge of the clock. What do I see? What's my input? I see a 1. So where do I go? I stay in C. And my output stays 0. Because in C, my output is always 0, regardless of the decision. Okay, now where do I go after that? What do I see? Yeah, because I see that 0, so I go back to B, but we're still at 0. And then what happens next? Yep. Yeah, exactly. And what is my output? What? Because I was in B, I saw an input of 1, so I make that transition from B to A. That's my state machine. Now, I could describe what the state machine is doing more or less. Let's puzzle it out, right? It's basically saying, do I see well, in this case, I assert an output if I'm in A and get a 0, which happens if I have like a long string of zeros, right? And I also get it if I see a 1 after a 0. So it's really just detecting various sequences of numbers. This is what we would call a sequence detector that tells you 2 different bits of information. Later on, I'll have you guys build like real sequence detectors that like ask you to find, like assert a 1 if your sequence is 0, 1, 0, 1 or something like that, right? They're really good at this, detecting sequences. But you don't really have to know what it is trying to do to evaluate it, right? It's just timing diagrams. That's why they're important. Part of the reason they're important. Okay. Now, you can use don't cares in state machines. So what that would look like is okay. This is like this really simple state machine, right? And we tend to use dashes as our don't cares in a state machine. And what this is saying is if I hang out at A, I assert a 1. So as long as I'm getting strings of zeros, I'm 1. If I get a 1, well, then I instantly bounce to B. I turn off my output, but then no matter what, whether I get a 0 or 1 next time, I bounce back to A and assert 1, right? This is a really simple state machine. But let's go ahead and talk about the next tool that we have for describing this state machine. So the next tool that we have, this is actually like the best tool to start out with because it's very human readable and very intuitive and very easy to change if you decided you don't like your design. The next tool is a little bit more design friendly. Once you've decided what your state diagram is supposed to be, we can use a state table. And what it has is a current state, a next state, where are we, where do we want to go, and what are our outputs. Now, in both the case of next state and output, we don't only care what our current state is, we also care what is our input here, right? So if I'm in A, to decide where I go next, I need to know what is my input. Well, if my in, and I'm going to call it W, just because I did in my notes. If I want W is 0 and W is 1, right? Those are my options. And what this says is if I'm currently in A and W is a 0, I stay in A. Otherwise, go to B. And then my output is similar, right? It wants to know what is my current state and what is the input. Well, if the input is 0, I get a 1, otherwise 0. B, we're going to do very similar, right? So B is just saying if I get a 1, I go back to A, otherwise C. And then C is if I get a 0, it's B. If it's 1, I stay in C. All of my outputs are 0 except for this one and that one. So I'm going to say, well, if I'm in B and I get a 1, so I'm in B, I get a 1, my output is 1. And that's all a state table is. So it's a description of where am I, where do I go? Now, I'll come back to that. So really Wish I had two boards in this room, but this is okay. Let's go ahead and start a different example. I want to leave up these two for a bit, but I'm going to shrink them down just a bit. And what we're going to make is an adder. And we're going to do this as a serial adder, which makes sense, right? Because if I'm trying to add two numbers, I can do it serially. That's how we really do it as humans, right? We go, well, what's this column? It's a 1. Okay. What's this column? It's a 1. What's this column? What's a 0 with a carry? How do we do that in a state diagram? Well, we have some simple decisions. We get a, let's start with 0, right? What happens if I have two inputs, right? So this time my input description is going to be I'll draw it here. In 1, in 2, / out, right? That's going to be the structure of this. Well, if I get a 0, if it's 0 plus 0, right? 0 plus 0, my output is 0. Similarly, if I get a 1 plus 0, a 0 plus 1, then my outputs are 1 on both of these, right? So 1, 0 or 0, 1, my output is 1. Now we need a little bit of a special case for 1, 1, right? I don't get to hang out in this state always. If I get a 1, 1, I'm going to go to state 1, which is my carry. What happens when I have to carry? I have to hold on to an extra 1, right? So in the case of 1, 1, and let's think of this the first time, right? In the first column, if I get a 1, 1, and this is also how I'll design state machines overall, is just start from the beginning and think, where should I go, right? What happens if? Okay, well, if I get a 1, 1, my output is 0. So that means 1, 1, my output is 0. But I have a carry now, right? So what happens if I'm in state 1? And we know two things are going to happen. It's either going to stay or it's going to go back. Okay, so if I have 1, 1 and I have a carry already, right? So this case. Well, I went 1, 1, 0, and now I'm in S1. Well, it's 1, 1, and 1. So in the case of 1, 1, I'm going to have a carry, right? So that means my output is 1, and I still have a carry. And that's what staying in S1 means. I still have a carry. Okay, well, if it's the other case, and I have a carry from the previous one, but it's 0, I still have a carry, right? 1 plus 1 is 0 with a carry, and state 1 is with a carry. So 1, 0 or 0, 1 stay here, but output is 0. There was see because it's 1 plus 1 plus 0. There's this implicit plus 1 in here. That's what's happening, is 1 plus 1 plus 0. So my output is 0, but I still have a carry. Okay, well, if I have then 0, 0 with a carry, well, now my output is 1, right? But I no longer have that carry. So I leave the with a carry state. Right? Once I have a carry, the only way to get rid of carry is 2 zeros. Does this make sense to everyone? This is a two-state state machine that has the ability to add any number of bits, right? Now, kind of what it's lacking is a reset, right? There's no way to kind of just reset in the middle of it, but so again, you'll notice what I did over here, how that one circle has 3 options. I could have done this over here. I just wanted to start out kind of a little bit more explicit with the descriptions, but I don't actually need this loop, right? Still conveys the same information. In any one of these 3 cases, we stay put, but our output might be different. Well, now my output has to be attached to something, right? Because I'm getting 1 bit at a time. Can anyone think of a nice, useful component that we've talked about that we could plug this output into to keep track of what our result is?
Well, I was thinking maybe we could use a register or shift register.
A shift register, yeah, exactly. So a shift register says, get the result and then move it over, right? So it's gonna be sitting here and waiting. And let's just say it's 4 bits. Well, what's gonna happen is, if I'm doing this addition, it goes 1, 1, okay? Well, 1 plus 1 is 0 with a carry. So it moves over into state 1. Then it goes, well, 1 plus 1 is 0, still has a carry. So this 0 then gets bumped over because we get the next clock cycle, right? And that's what shift registers do, is they shift 1 on a clock cycle. So he bumps over, and we get our next 0, right? And then the next clock cycle happens. Well, 0, 0, but we have a carry, so we bounce back, and we get a 1. So now these 2 bump over, and the 1 slots itself in. And then let's say we just have like a 1, 0 or something hanging out here, because I said 4 bits. So actually, the 4 bits make sense anyways, right? So then I have an implied 0, 0. Nothing else happens. They shift over. Ta-da. Right? That's how that would add. Now, the downside to this, does anyone see what the problem with this is compared to even the ripple adder? Yeah.
Is there no exit condition, or because
that's true, but that's not what I'm quite looking for. Speed, right? This one takes a number of clock cycles equal to however many bits I do. But I've already established that our clock to Q delay is always slower than a comparable number of gates, right? So unless our ripple carry adder is, I guess, massive, even then I doubt it, it's going to still be faster than this, because it just gets to compute all of the bits as fast as it can, whereas this is 1 bit per clock cycle. That clock cycle has to be, by definition, slower than an AND gates delay, or even 2 AND gates delay, right? Or AND gates delay, you start getting questioned a little bit. You're just not gonna, have that, and that's per bit, so it takes a long time. They're not very fast. It's elegant, it's pretty, but it's not fast. Okay, and then we could go ahead and we can make a state table out of this. This only has two states, so it's easy. Same kind of idea. So it has a current state, a next state, and an out. But it has a bit of a difference here in the next state and out because we have actually two input bits, right? So we could have 0, 0, 0, 1, 1, 0, or 1, 1. And then my out has the same issue. But now I can go and fill this in. There's only two states, S0, S1. And in the event of, well, 0, 0, 1, 0, or 0, 1, we stay put. Right? And then if we're in state 1, in every case except for 0, 0, we stay put. And then we just do the same thing. What are the outputs doing based on their current inputs in the current state? Anyone need me to do that? You do? Okay, so we're at current state is S0. If my input is 0, 0, that means I'm here and I get this 0. Same thing at S0. If my inputs are 1, 0, or 0, 1, my output is 1. Keep going. If I'm in state 0, I see 1, 1 as my input. My output is 0. And then we go and do the same thing for this guy. So 1, 0, or 0, 1, I get zeros. And then 1, 1, or 0, 0, I get 1. Okay. Are we okay if I erase this? So everything I've explained so far is actually one particular type of state machine. That type of state machine is called a mealy state machine. There is another kind called a moored, with two O's, moored state machine. Now, the quick clue in this is actually if you're, one of the differentiators is, as a general rule, more state machines take more states to implement. However, they're simpler. Why are they simpler? Well, in the case of the Moore state machine, it doesn't care, the outputs specifically don't care what the inputs are. They only care what state it's in. I'll say it a different way. The outputs do not depend on the inputs in a Moore state machine. only on the state that you're in. So like in the state table, this is a mealy because my output cares W0 or W1. It cares what my input is. A Moore state machine would just list the output. What is the output when I'm in state A? Completely oblivious to what's happening. So a way to draw a similar Moore state machine, actually I'll draw it correctly. All right, this is actually the same state machine. So this bar, this line, isn't trying to divide a thing. What it's saying is the output is 1. And then the transitions are the same, right? They're evaluating what is the input. If it's a 1, go to state B. If I'm in B and I see a 1, I come back to A, and then my output is 1. Now, there is actually a subtle difference when you went with, if you were to go and implement this. Anyone kind of think maybe what the difference is? Because in this case, it's actually the same number of states. You'll notice that it doesn't always have more states, but it tends to. We can even see kind of like a difference that happens. It's subtle. It's okay. It's actually that the output can change at different times. So if I was in state B and my input were to change to, so it was a 1 and I go to B. My input while I'm in B, if it's a 1, the output could actually instantaneously change to 1, but it couldn't update state till the clock happens. Because my output is determined by combinational logic. And so if my combinational logic says if I'm in B and I see a 1, assert 1. So that could happen instantly, right? Whereas here, if I'm in B and then the inputs change it to a 1, nothing happens until the next clock cycle allows me to move back to A. Now you can design it either way. You could actually design this to behave that way, but you cannot design this to behave that way. That's a little bit more of an advanced idea. It'll make more sense in 3610. We'll tinker a whole bunch with that. And the way to kind of talk about it, let me, 1 second. How far away is this discussion part of this? I'll skip ahead. I'll end up mentioning this again, but it's because the state machines have 3 parts. They have the next state decoder, which is combinational logic that decides where am I going next. Next state logic is combinational. The next thing it has is an output decoder that says, well, what is my output? That's combinational logic that takes the state and the input in the case of a mealy, or just the state in the case of a Moore, and outputs it, right? The types of inputs to this combinational logic are different between the two. And I'll give you a visualization of that later. And then the third part is the current state, the remembrance of where are we now? And that's just D flip-flops usually. Okay, back on track. So another thing that we can do, similar to how I showed you that we could use don't cares, we can, instead of writing 1s and 0s, we can just write signal names. Well, let's say my output is, let's give it a name of Y. So in the case of A, I have Y. In the case of B, I have not Y. And in the case of C, not Y. And I can do the same for inputs. Right? I can use signal names in place. And in fact, I could go further if I had more inputs, right? If I had lots of inputs, it could be like W or Z and F or something like that, right? It could be a logic expression that tells me when to move to the next one. For now, we only have one input. It's W. It's not fancy. Okay. Another thing. Oh yeah.
So why are we using why not with C when, well, when I mean, I would expect it to just be like 0 or, oh.
It's going to output. We're saying if Y is active high, then not Y is 0.
Okay, sorry.
Yeah. No, it's okay. It's a good question. And I did forget this one, right? This is W. It's just evaluating is this expression true or not? And then the output is saying, am I outputting true or not? That's all. Yes.
Doesn't A need not W as well?
Oh, yeah. The completion. That one you mean?
Yeah.
Yes. Yeah. So what's interesting is technically I don't need that. It's just that would, without this, it becomes an improper state diagram. So a proper state diagram expresses all inputs and outputs, whereas an improper can kind of just be the bare minimum. And so like, it's a good way to example this. So let's say I had a second output called Z. And let's say I only wanted to do assert Z here. Well, there's two ways I could do it. If I needed Z to be 0 in A and B, then I would have to write not Z. If I don't really care what Z's doing in those other states, I could be like, well, don't care or right, not Z, whichever one I wanted. But once you get to design, this really is going to be a don't care, which you don't really know if that's going to be a 0 or 1, and it may vary depending on how you got here. Which, so you just have to be careful with that, but you can use don't cares, or you could just kind of leave them off. Leaving them off implies, especially on an output, that you don't care what that output is right then. On an input, if Z was instead an input, again, let's say I don't care what Z's doing. I don't care what Z's doing, but here I need not W and Z. So here would be this, sorry, not Z, to make that transition. So this W, you kind of have to have this implied, I don't care what W is doing, sorry, Z is doing, right? So it's W don't care is the implied. Then the issue is now, actually is that okay? Yeah, I probably need a third circle to describe what happens in the case of not W, not Z. But if I wanted to be fully proper state diagram. Okay. Make sure I'm back to this guy. All right, so there's something else that we have to do because we can't store integer logic NA, right? Because we only have zeros or ones. So much like the opcode that we've already built inside of our project, right? You want to have a assignment, a binary value associated with the name of the state. Now, the reason you want to use A, B, and C like their names is because they can be descriptive. I want to be in idle, right? But you want to, the name has to be associated with a binary number, like 0, 0. So, and this is where I saw maybe the most problems on the project actually, is people wrote the constants to have that, right? So you would write something like, right, constant A is a standard logic vector of size 2 that is assigned to 0, 0. You write the constant, but then in your test benches, you didn't use it. You wrote 0, 0 a bunch. Well, in the case of the opcode, 0, 0, 0, right? That was the reason I wanted you to use these constants, is because I wanted you to just write your opcode. Write add is a lot more clear than writing 0, 0, 1. Just like if this was an idle state, calling it idle, so I have a code that says when idle, do this. It's a lot cleaner than when 0, 0. What is 0, 0? It's not readable, you know? Okay, so we have to have enough bits to fit all of our states. But I have 4 possible states. So there's this implied 1, 0 hanging out in here, right? That's a possibility. And its state, we're just gonna call, I'm just gonna call it delta to very differentiate it from everything. And then its next state is don't care, because I should never be in that state. Well, its current state, don't care. What is its output? I don't care, I shouldn't be there, right? So it's this whole state of I don't care what happens if I get there, because if I did, something went wrong. Now, unfortunately, through timing issues, you may accidentally end up in bad states. If you end up with weird timing, which we'll talk more in 3610 about how this happens, all you need to know is how best to minimize the chances of it happening. And you do that with 3 simple rules of assigning numbers to your opcodes. So the 3 rules. Number 1, states with a common next state should be adjacent. What adjacent means is just the next number, right? So if I have, I'll illustrate these because they tend to be best illustrated. So I'll say it again, states with a common next state should be adjacent. So if I had a situation where there was, say, A, state B, and they could both go to C, A and B should be adjacent because they have a common next state. Then, and this works because 0, 0 and 1, 1 both have a common next state of B, and they're adjacent. 0, 0, 1, 1 are adjacent, right? They're the next number. Adjacency in digital counting is cyclic. And that's why this is 1, 1, not 1, 0. And these rules kind of flow in order of priority. Okay, the next one is states that are the next state of a common state should be adjacent if possible. If this were to be true, D and E should be adjacent if you can. And lastly, and this one doesn't apply in this one because the example doesn't come up, but states that have the same output given the same input should be adjacent. So if I had two states that were given 0, 1, they output Z. Well, they have the same output with the same input. They should be adjacent. This is a lower priority situation. Wow, time flies sometimes. Okay. How do I want to do this? Yep, I'm going to erase this one. Okay, so now we're to this part that I kind of jumped ahead to earlier, where we talk about the three main parts of our state machine. So our state machine has the state register, which stores where are we now? What is our current state? It also has, the next component is the next state decoder. Combinational logic that says where do we go next? And the output decoder. Combinational logic says what is our outputs? Now, this is actually a fairly easy to draw concept. So let's start with that state register. And it says, I'm going to call it the state register R. Where are we now? It is sequential logic, so it has a clock. And it has an input of next state, because when the clock happens, it will update to whatever next state is. When it does update, the output then is current state. That is our state register. It's really easy. It's nothing new. Now, the next thing that we have is, I said we have this next state decoder, the next state combinational logic. Well, this next state decoder, I'll call it NSD, next state decoder, it has multiple inputs, right? Well, it has an input that comes from external to the state machine, right? What are our control signals that are driving this? The next input that it has is it needs to decide what is our next state based on not only input, but also where are we now? That's all. And then the next and third piece, third and final, is our output decoder, OD. Now, if we're a Moore state machine, we're done, right? Because the output decoder only cares what our current state is. However, if we're a Mealy state machine, we also care about this path. What are our inputs? That's all. That's all a state machine is, those three blocks. Now, when you write it in VHDL, you'll sometimes combine some of these. So like, especially in a Moore state machine, a lot of times your current state register is combined with your output decoder, because if it's that simple, you just link them together, right? You can picture it similar to the MUX example that I gave when I wrote a process, right? So you have a process that says something like, when you're in state A, output is Z, right? That's all. Okay. But how do we make next state logic and the output logic? How do we make it? Well, let's think about this. How many bits does our next state decoder have controlling it? How many input bits does NSD have? You all managed to get it wrong. 1 bit input, 2 bit state, right? However many bits we have. So if you have lots of states, this next state logic gets really complicated. 2 bits. So let's go ahead and write our favorite thing in the world, a 3-bit K-map. Because K-map is how we make combinational logic. And now that we know how many inputs we have, well, I'm going to call my CSQ, and I'm going, well, I'll leave that as now, input. Yeah, and the next state will be D, just to differentiate them. So my input to next state decoder is going to be Q1, Q0, and W. And now I just have to fill in the K-map, right? So let's look. If my current state is 0, 0, that's that first column. And so my results then, Y, so this is going to be for Y. And do the output decoder first, it's a little easier. Okay, well in the case of 0, 0, I get a 1 or a 0. In state B, 0, 1, I get 0, 1. In the case of 1, 1, both are 0. And the other state is I don't care. Right? I should never be in that state. So then, this is a good review, right? Because we're going to throw K-map on that exam for sure. Just part of the design. Write out this K-map. Well, what doesn't change? Well, the W doesn't change. So Y is equal to not W. Oh, I didn't mean to do that. I meant to do this one. Good catch. Okay. Not W and Q0. Or, well, W, not Q1, Q0.
W not Q0, right?
Yes,
Or not
W,
yeah,
not Q1 is Q0. Am I wrong?
or so for the not W Q0, should that be not W not Q0?
Oh, yes, I see what you're saying. Well, our next state decoder, NS, which we're going to call D, which is 2 bits, we have to be careful, right? 2 bits. D has 2 bits. That means we need 2 K-maps for it. 1 K-map per bit, right? We haven't learned how to do a K-map that has multiple outputs. If we have multiple outputs, we need multiple K-maps. Each bit is its own output. Okay, now, where do these values come from? How do we fill this in? Well, it's because in this next state, A is really 0, 0, and B is 0, 1, C is 1, 1. Right? That's what's implied. That's what those values mean. Now, it's nice that I can just write A as my next state instead of 0, 0. But for now, it's more illustrative for me to point this out to you by drawing it out. Hopefully, this starts linking the name to the number, right? And hopefully making clear why I care about the name. It's because it would be tedious, especially if I start getting 4 bits, right? That gets tedious to write compared to A. And it's still true in code. Okay, then the next thing is we recognize that Q0 are those bits, which means D0, meaning the next state vector, right? D, this guy, are those bits. All right, let's start filling in a K-map for D0. Well, it works the same way, where this is my state, and I still don't care what happens in either one of these if I'm in state delta, right? That 1, 0 column. Other than that, I just start filling in the columns, right? Because column 1 is 0, 1. In other words, D is supposed to be 0 if W is 0, and 1 if W is 1. And now I'm just going to fill in those K-maps for the rest of these, right? 1, 0. 1, 1. And then the same thing for the ones that aren't underlined for D1. 0, 0. 1, 0. 0, 1. I would then grab my marker and start saying stuff like, well, let's simplify me a K-map. I've got a cool 4 here. And then the best I can do is this one and that one. And this guy is very similar to the other one. And then we can write expressions for that, right? Get some circuits. And then I would take those expressions and plug them into circuits and plug those circuits into these, the NSD and the OD, right? We'll do this some more. This is going to be definitively an exam question, not this exact, obviously, but the same kind of thing, where I'm going to do something like, given this state diagram machine, please draw me the next state, or sorry, the question will read something like, given this state diagram, not this one, but some other one, draw me a state table, and then derive the next state decoder and output decoder, and then draw me the complete state machine. That's the kind of question I ask. Now, we have several weeks, and the only thing that's left to talk about really are state machines and microprocessors as a whole. So we've got lots of time to go back and kind of cover this. So don't panic too much yet, but just be aware, this is where we're going. This is where we bring everything together, right? This is combinational logic, remembering where we are. It's using K-maps, given inputs to design logic. And then we're going to start asking the question of, what is the timing diagram matter for like the delays? How fast can the state machine go based on the delay from the output into this feedback, right? We're gonna start bringing all of everything together when we build one of these. Okay. I guess it bears just illustrating a little bit. This D vector is 2 bits, right? That's D0, D1. Inside of this register block, then has to be 2 D flip-flops. And then inside it would break out to something like that. And then they join together to be that output, right? That's all that's going on inside of the register block, is 1 D flip-flop for every bit required to represent all states. Okay, I've got a couple of examples that we'll start off with next week. For now, that is the hour and 15-minute mark, which is perfect, actually. Any questions or confusions on this that I can clear up right now? Okay. Okay, so as I said at the beginning of this class, this exam is going to be 1 hour and 15 minutes. I would very, very much prefer that everyone take this one in person. You can, of course, take it online remotely if you end up with COVID or sick or whatever. I'll post it online. Prior to the previous exam, I posted that the majority of students that took it online last year did a couple of percentage points lower than the people that took it in person. In my 2 classes this semester, for whatever reason, almost everybody that took it online bombed it, like terribly. And I don't know where the disconnect happened. There was a couple of exceptions to that rule, but I think this online learning thing, people trying to do things remote, has kind of like caught up with everyone just like mentally and emotionally. So try and show up. It's making a big difference. I don't know if it's like parents and siblings and dogs distracting, or if you're just not in the learning mode when you're at home. Whatever it is, it's just been devastatingly unproductive for a lot of students. So it's up to you ultimately, but it's proving to be better off if you show up here. It is also, the way the exams are written, it's a little bit quicker to do everything just by filling it in by hand, because that's how they're kind of written. And I'll go over what the material is essentially going to be, what the exam questions are going to be. And I'll try and stick pretty close to what this review goes over. If I sometimes afterwards I come up with like a really good question idea, but it will still pertain to concepts here. Okay, that being said, I'll start off with like a quick overview of, I haven't written a test yet, but I have written like the bullet points of concepts I would like to test. So Those include especially timing diagrams. There will definitively be more than one timing diagram. There will probably be at least one that is combinational logic, meaning just nothing but gates, no flip-flops, no clock. And there will be at least one that is combinational, so it has a clock. There will be at least one of each of those. There will be a design problem where I will present something to you that will say something like, design me a circuit that does X, right? And there's a good chance, I believe, that this is where I'm going to insert either generic, well, and or maybe both, generics and generate statements. I think that's going to how this question is. I'm going to say, design me blank using a generate statement. And I may or may not have it like, so like the example we did is an n-bit shift register, right? So I may ask you to build me an 8-bit shift register using a generate statement. That's different than saying, build me an n-bit shift register, right? So if I say n-bit, if it's variable, you need a generic. If it's not variable in size, it's just generate. Something that I love doing, and I will do this on this exam and I'll do it on the final, is I'm going to give you guys just like snippets of code with a description of what it does, and then I'm going to mess it up. And I'm just going to say something like, there are at least 5 errors in this code, please find them. And then you just go through and circle them and identify them. Now that's another reason that the in-person is a little bit faster and better, is because if you are in person, you just circle it and point an arrow to it. Whereas if you're remote, you have to type out, usually, depending how you do it. If you print it out and write on it, might work fine. Like, what is the error, you know? I will definitely have something like that in here. And that will be testing essentially that you understand syntax, right? It's going to be simple things like missing semicolons. It might be mismatch in vector sizes. It might be, I forgot to declare a signal, that kind of thing. I am going to ask questions about shift registers, counters, and flip-flops. Now, I'm going to do examples of all of those types of questions here today. And if I don't get to those, then I'll just post the questions that I was going to ask so that you can practice them. So you'll get an idea of what I intend to ask, but make sure you understand how counters work, how are counters built, how are shift registers built, how do they work, what do they do, and what are the different types of flip-flops, how do they behave, make sure you can draw the timing diagrams. Now you've gotten practice with all of those, right, in the recent homeworks, so hopefully those aren't a surprise. I'm going to definitely ask some question that involves muxes. I'll do 1 or 2 of those today that kind of example, because muxes are really important and freshmen tend to struggle with them. I don't necessarily know why, but they do. So I'm going to ask, I'm going to test, this next bullet point kind of ties back into my timing diagram. There's going to be at least some part of it will have propagation delays, whether that's clock to queue or just gate delays. And we haven't done a lot with them, but they're not too hard, and I'll cover some of that today. In the review, I could ask you questions that are, is this circuit synchronous or asynchronous, right? Or is this reset synchronous or asynchronous? That kind of thing. So make sure you know what that means. And there will be a question that'll tie some of this together. I think I'll do an example today. At the very least, I'll review it. Then we'll just talk about, this is one of the first things we talked about after the last exam, which is the addressable memory, right? Which is where you give it an address and it gives you a value. I'll review that today as well. So we can do, it's not going to be a super complicated question. It's not something I put a lot of weight on in complexity, but it is something that I am actually required to teach and test on in this course. So it has to be there. So sorry, but I'll keep it relatively not too painful. Yeah, those are my bullet points for what we're doing. So now we can dive into practice problems. And I've kind of identified where I think you guys' problems are, so I'll start off there. if there's something that you guys get to and you're like, I need more information on X or something, then I'll do it. Okay, let's do something. Yeah, this will work. Actually, I think I did this one. Let me skip this one. Let me do this one. This is basically, if you look at it really carefully, it's basically an adder that I've just ANDed the two output gates together for fun. I didn't want to do two different outputs. So anyways, the way that you're going to do this is generally, right, I'm going to provide you with a timing diagram figure of some kind. And then I'm going to give you, I don't know, I could say it a couple different ways. I could say exhaustively test this circuit. If I say that, it means I need all possible input combinations, right? I may go far. I learned my lesson from last exam, and I may specify the order in which you do them, because grading them got kind of tedious, to be honest. So I don't know. I prefer to do the LSB first, the least significant bit, the thing that changes the most. So that's how I'm going to do it here. So I'm going to say A first. Pay attention. If I tell you to do it in an order, make sure you follow it, because I'm going to mark you down because I'll be annoyed. If I don't tell you in order, that's my bad, and you can do whatever you want. If I'm really smart, maybe I'll actually just give you A, B, and C so that you don't have a choice. I don't know. We'll see. Regardless, I need to test all possible input combinations of A, B, and C. They're not going to have any type of delay, right? Because these are just the raw inputs. And the way I do it is I just start there, and then every 2 is where this one changes. 1, 2, 3, 4, 5, 6, 7, 8. I did 2A. Right, because it's 2 to the 3. It's only 3 inputs. So this question just kicked the crap out of everybody in the last exam. So A, B, and C, right? There's some points. We're done. Just kidding. And now I may say something, especially on this exam, I didn't before on the last exam, so I can add this in this time, and probably will. I will say something like, T delay is equal to, I don't know, 10 nanoseconds. And then I would say each division or something is 20 nanoseconds. So each gate delays half of one of these dashes. So you can see that might start getting kind of interesting, right? Because I'm changing A really fast compared to having a possibility of 1, 2, 3, 4 gate delays. So maybe I should specify this at 5 nanoseconds just to keep like completely weird stuff from happening. I'm trying to decide if this is actually going to be an issue, because 10 nanoseconds is a lot easier to draw than 5. Let's go with 10. Let's see what happens. We'll do it. 10 nanosecond delay. So it's half of one of these periods. All right. Then the next thing that you definitely want to do, if I don't for you, which I should, I did in the first exam, and I'll try to remember this time, is label the nodes, right? Give them names. D, E, F, G, H. I guess that makes the output I, sure. And now we can go ahead and start putting these out one at a time, right? You're not ever trying to puzzle out this whole circuit. That would be insane. What you're trying to puzzle out is one node at a time. And once you have a node, right, F cares about C and D, nothing else. It doesn't have to care about C, A, B, all of those. That'd be complicated. So let's do it. Let's do D. Okay. D is just A XOR B. XOR is true when they're not the same, right? So I'm just going to go ahead and find the spots where A and B are not the same and mark those as true. True. A and B are not the same, are the same, are the same, not the same. Not the same, are the same. Now, it turns out that it's actually going to be easier for me to do F before I do E, because now I'm just comparing D and C. And that's just an AND gate, right? Nothing hard here. It's just when is D and C both true? Well, because C moves slowly and I don't have anything until way over here, D's there, so F isn't true until there. Did everyone see what I did, right? Is I just found one that was easy to look at. And I know the output can't be true unless both are true. And then went from there, right? Low hanging fruit and all. Now E. E, I guess I could have done this as quickly as well. Let's look at E. Well, E is true when D and C are not the same. That's these two. Am I messing any of these up? Let me know. So here they become the same again. Okay, so I've got D, E, and F. G is simple and boring, isn't it? Because G is just A and B. So when is A and B? Well, I can start by looking at B and say when it's true, because it's a little bit slower, coming all the way down and saying true there and true there. otherwise false. Oh, guess what I did? I forgot the delay. We'll do this one without delay first, and then maybe we'll go back and revisit with delay. Let me think about this 1 second. Should I just back up and do this with delay? Because that's kind of important. All right, D. We'll start with D and fix the delay. D has 1 gate delay from when either A or B changes. Right? It takes 1 gate delay for it to update. So here A changes. So really anywhere D changes is where I'm looking because that's what's interesting to me. So if D changes after 1 gate delay is halfway through one of these periods. That's an easy fix. F. Now F has 2 gate delays if A has changed. Right? So F has to worry about the change in D. So we'll just look for where does D or C change, which means where does F change? Well, this can be a little bit complicated. So I know this dashed line is where it's supposed to be true. Everywhere else is false. Well, let's look what happens. We're D and C. Well, that didn't affect anything. This could have, right? If this had happened a little bit earlier, you might get a little bit, but it didn't. And then this one is affected because instead of changing on this mark, D didn't change until here, which means since D didn't change until here, my F can't change until 1 gate delay after that, here. So now it looks like we've pushed off way far down. This is okay because at H, I don't have to care what's happening prior to F. I just deal with F's delay, right? As long as I did F right, everything else is right. Well, can be right. Okay, E. I'm going to start off by dashing this line. And I'll bust out an orange to make it apparent. So E now changes as a response to D XOR C. Okay. D XOR C. Here is where that change would happen, but I need a gate delay after that. So I am there. Okay. Here is where they're no longer different. So 1 gate delay after that, it can drop to 0. Okay. C or D. Now what's interesting is at this point, they are once again different. Oh, sorry, let me redraw that one because it's this line. They're now no longer, sorry, they are different once again, right? So let's puzzle this out. So E is going true because they're different. False because they're the same. And then here, one delay later, it's true again because they're different. Right? So different, same. This region is same. Different, same. So we drop. Different again, so we rise. And then the next time they become same is here, which is halfway through. So I'm going to be a little more careful to draw that halfway through down this line. One gate delay later, it drops. So if I do gate delays, which I probably will, I'll give you more time. I'll estimate more time, right? Because this is harder. And you'll notice that it is actually kind of interesting when the delays happen. Did I screw this one up? Should this be one more half delay later? 1 o'clock. So we dropped halfway through this one. We rise halfway through that one. But this rises. Oh, that's why. Because this one doesn't have any gate delays. Right? So because it doesn't have any gate delays and D does, we've actually changed the width of this drop. Someone thinks I'm wrong, but I feel pretty good about that one. Okay. Now let's do G, where G is, oh, A and B. So it's just one gate delay. That makes it really easy. I'm going to write it right below so everyone can kind of see. Right, just half of one of these tick mark periods because that's one gate delay. Okay, now H. H has one gate delay from F and G. But F and G, I don't have to worry about where their delays came from as long as I match them to what's happening. So let's look at F and G. And it is F or G, right? So if either one of them is true, H is true with a half period delay. So what does that mean? Well, we go here and I say half a period after this one, H can go true. And then half after this one, it drops back false. And then from F, we have half a clock delay here where we're going to jump back true. Okay, that one wasn't too painful. Wait, G rises, half a clock delay. Now we've got E and H, we can do I. And who knows what I is going to do, because this is kind of weird. We're saying E and H. Okay, so all the way till here, we're definitively no. And in fact, we transitioned to 0 at the same time this went, so we're still no. And finally, at this point in time, this midpoint, it looks like, let me grab a new color, red. This midpoint color is where we have E and H. But we only have E and H for half a period, and it is delayed by 1 period. So no, 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 no. Delayed by 1 period is true. But then, half a period later, this is dropped to false, so we're back false. So now we can look here, true, it's just gonna be false. If you guys end up wanting to be sure, double check that I'm right. When you go home, you can go ahead and pull up Vivado and write gate delays, right, using the after. F is equal to D and C after 5 nanoseconds, or well, 10 nanoseconds, sorry, right? And then when you ran the simulation, you'd get this, hopefully. So you have a tool to go check now, right? You're pretty confident in Vivado by this point. That's all you would do. Okay, are we good if I move on to our next example? I think I used that example. I'll move on to something else, a different topic. I'm going to take a note to post this if I don't get back, if we don't come back around to this other timing diagram example. Oh, something I might do to you guys. It's actually pretty likely. Like here I have this AND gate kind of thing going on. Something that would be kind of fun in this timing diagram, because you guys are more competent engineers than you were before, is to do something like this. I'll just draw up like a kind of dumb circuit. I don't know if it would do anything, but instead of what we had before and an AND gate, I could do that. Right, where now B is acting as a select signal for the mux. You know, that's within your capabilities. Because all this is testing is making sure that you paid attention to propagation delays and what the devices do. So something like that would be an example of what I might do to you guys. I also haven't ever thrown NAND and NOR gates at you. I could easily do that as well, right? Instead of just AND and ORs and XORs or XORs. Okay. This one. I like this one because it's kind of simple and obvious once you get into it. I love questions that make you guys panic and then you realize if you prepared that it's not really an issue. Okay. So this question would read something like, a D flip-flop has its Q output connected to the J input of a JK flip-flop and Q bar to the K input. The input sequence to the D flip-flop is 1001. Draw the Q output of the JK flip-flop. You guys want me to walk through this, or you guys want me to give you a minute to do it? I'll give you a minute to do it. Go for it.
We're assuming this string is being fed at every uptick or every rising edge of the clock.
Yes, exactly. Yeah, the input sequence means you get one of these bits each time a clock is risen. So if you were to draw it out, right, the clock is doing this. And an easy way when I say input sequence is, well, here's each of those rising edges, right? It would be 1, and then just transition on the falling edge. And on my exams, they're always rising edge triggered devices, unless I say otherwise or do the little bubble thing, right? If I have a bubble next to the clock flag, it means inverted clock or falling edge clock. So 1, 0, 0, 1. That's the input, clock input. almost done, everyone, looks like. Does someone want to just come up and doodle it for me? Have a brave soul. Go for it. Or grab a marker and finish the timing diagram.
That's,
Black one should be okay.
okay.
Yeah. So that's our cue, right? It's just the 1 clock period delayed of the input. Does anybody want to then, so if Q is that, then Q bar is just the opposite, which is, and happens at the same time as Q, so it's low, high, low, which means another way that we could call these is J and K. Right, because Q and Q bar are going into J and K. Or did you do the final Q?
That was the final cue, but
Oh.
it should be,
I think they're the same,
yeah, they are the
but
same.
one more clock period delay than what you had, weren't they?
Assuming reasonable delay. Yeah.
So that's why, so it turns out that Q, this Q, which is the J input, and that Q are the same, just delayed by one more clock.
Yeah, I guess I assumed it was all synchronous.
Well, they are, but they, so remember that it helps that to assume that you have like a tiny bit of delay, just like some arbitrarily small amount. So that you don't, because it doesn't just flow through instantly.
Right, right.
So it is 2 clock delays from that. Okay, is all. Yeah, so I'll walk through that real quick. So if this is this is J, then when the clock hits, J gets defined for the first time, right? You don't know until this rising end of the clock. When it does, it updates to whatever D was with a little bit of just a little bit of delay, right? It can be arbitrarily small. It just helps you students generally to see that small delay, and it follows with a little bit of delay. Now, the timing technically works. If I don't have delay, it's just easier to see if it does. So then the same thing happens now if J is doing that and K is the opposite of this, then when the clock hits, well, this first clock, I could argue, I don't know how the final output Q. I didn't know here for sure. And the first clock is taking whatever the output of Q was before, which I don't really know. It could have been a 1, it could have been a 0. But it does on this clock then update to my J and K inputs, which are 1 and 0, which our JK is these two can never happen, right? Because our inputs J and K are just inverted, and then 0, 1. So really we've configured this as a set reset latch. Sorry, set SR flip-flop is what that JK is actually doing. And then when it happens, we can kind of see where this is. And so we get a 1 and a 0. 1 on J is 1. Next clock happens, it's a 0 and 1, so reset, right? And then again, we want to think of this as being a little delayed just for clarity. And we get a 0, 1, J is 0. So we're still 0. And then there's, I screw this up. Do I need one more clock? Probably. And then this clock finally can update to 1 on J. So it is this, the input.
Shifted over another.
Shifted.
Okay, well then,
Anyone get that? Close, almost. Yeah, so that's, be careful, because that's why I kind of encourage these like arbitrarily small delays, is because I don't know how the best way to draw this. I wish I was an artist for you guys. If there's a change on a signal at the same time as the rising edge of the clock, what that's really implying is it's taking the value on that side of things, right? It's like the limit as it approaches from this side kind of thing is really what we're talking about. So, because otherwise it's kind of this issue of what is this value? And another way to think about it, if it helps, is that at this point in time, it starts to change, but nothing is instantaneous, so it has a little bit of delay. So even if this clock were a little bit slower, it's still going to pick like this point. But when it decides, if you remember from like our first lab, when it decides, is that a 0 or a 1, it's going to pick 1. And this is like the non-math, this is the physicsy reason that it's going to pick that side of the clock, right? Is because it's not an instantaneous change. And we're slowly getting to where the change is, but we're not there yet. So take what it was before. Does that help, that drawing? Okay. A question like this is pretty probable. That's right. That is more than one flip-flop attached together. And it could be in this form of a counter. You know, it could be like, here's a counter or something that counts in a weird order. Draw me the timing diagram, right? And but the whole thing isn't to trick you. The whole idea is to make sure that you know how the flip-flops work. It's just make sure you can analyze the flip-flops. You can also ask, probably will ask, here's a freebie if you remember, what's the difference between a flip-flop and a latch? Yeah.
Flip-flops have a toggle state. Do they toggle between 0 and 1? Or?
No, that's a T flip-flop. Kaylee, what is the difference between a latch and a flip-flop? It's the clock. Yeah, latches are just, they latch onto the value, whatever it is, right? So we have the SR latch that builds the flip-flop. And in fact, that's another way I might ask that same question, and I'll just draw it up. Is I could provide a drawing like this and ask you one of two questions. I could ask it, what is this device? When I combine all of these, what is this device? Another way I could say that is draw me this device. What is another way more clear is what is the schematic symbol for this device? Well, the way I do it is let's look at more or less what happens. One of my favorite things to do in this kind of thing is, well, I've got a bubble here and a bubble here, a bubble here and a bubble here. Let's simplify, right? And just make this two AND gates because the NAND thing is kind of pointlessly complicated. I made them go away. What is I1 doing? Kaylee, what is I1 functioning as?
Input.
Yeah, it's an input, but what is the purpose of this input? It's an enable, right? Because it's going to both of these these AND gates. Those AND gates can't pass any information. Neither of them can unless we're enabled. If they are enabled, well, if I0 is 1, then we get set. Oh, this is where I did make one mistake when I pushed this bubble. I need to move it, right? So, quick rule. If you have like paths that branch like this and you want to push out a bubble, you have to send a bubble down each path. And that's what I forgot to do because I pushed one there and I forgot this one. Okay, so if I have a 0 here, I'm not setting because I'm enabled. So I'm not setting. If I have a 1 here, I am setting. And I'm strictly only ever setting or resetting. Do we know what device this is yet? What is this device? The latch, right? It would be wrong to include a clock. There's no clock here. It's just a D latch. I have this in my notes, guys, right? When I was going through the process of building up the D flip-flop, this is one of the steps. I drew this exact diagram. So this isn't out of nowhere. So that's a fair game on that one. I expect that to be in your notes. Expect that kind of question where you start evaluating the functionality. Now, if you didn't have the ability just to look at this and go, oh, that looks like an enable. What's another way that you could maybe do this?
Set up a truth table?
Yeah, set up a truth table, provided inputs, and see if you recognize that truth table. Where I would say, well, if this is 0, the output's always 0. And if this is 1, then the output is just I0. And then you'd be like, well, maybe that whole thing is an AND gate. And that's not quite right, because that's crazy. So now I have to go, well, let's plug this into the set reset, right? because this is just the first stage. And then you would see that we're, this is the input, I'll call that alpha, right? And so alpha does this. It's 1, only if those two are true, we set. And that's kind of your clue, is we're setting there and only there. Whereas if we have beta, right? There's only one situation that we have alpha and one situation we have beta. In the case of alpha, I'm setting. In the case of beta, I'm resetting. Set and reset, and it just sets it to whatever the D value is. And then you would say Q is, well, if I haven't set a reset, right, it's just Q, whatever it was. We didn't change anything. And then this is the hard one. This is why it's kind of helpful just to recognize these structures, is because now I'm going, well, 0, 1. But really, another way of expressing that is just D. Right? It just matches I0. It helps most just to be familiar with the structures and recognize that if I have a latch already, I'm probably building another latch or another flip or a flip-flop, right? And what's my hint that it's a flip-flop if I have an SR latch?
Clocks.
I'm not necessarily going to have a clock, right? Because my clock, if I built it in, is just going to be like called I2. How many latches does it take to build a flip-flop? At least 2, right? If I have a D latch, I use 2 D latches to make a D flip-flop. And this is a D latch. So 2 SR latches with 4 AND gates, I can build a flip-flop. But if I only have 1 SR latch, it's still just a different kind of latch. So, and there's only so many things I can throw at you in this, right? I can do an SR latch, a JK latch, a D latch, a D flip-flop, a SR flip-flop, and a JK flip-flop, or a T flip-flop, right? I have a lot of different things that I can throw at you on this one. So when I ask you, what is this device? It's something that you know. I'm not going to invent something new, puzzle you guys. My job is to make sure that you know these structures, not something new. Okay. I don't know if you guys are just really clever and acting more puzzled than you really are, so that make the test easy, but 7:13. Okay, wow. None of this goes fast. I'll probably be posting some of these questions that I'm going to end up skipping. But I'm ready for the next question. Hopefully you guys are. So I'm going to combine this question, 2 questions into one in one go. This is another way that I will ask things. Is given that code over there, question number 1 is, what is it? Let's see. The other sense thing. This is a device you know. What is that device? And just give me a quick hand raise if you think you know. I know you think you know. I'm just waiting for at least one other person to puzzle this out. You think you know? You think you know? Yeah, you haven't answered anything in a while. So what is it? Is it D? It is. It's a D flip-flop. And it'd be obvious, right, if I had named my variables well, but I purposely boggled them. One, I like to do this to make students suffer so they realize what I go through when they name things poorly. But part of it is just being able to recognize the process of this. Like, what is the function of this block? Because you'll be shocked how often you end up doing something annoying like this, where you get someone else's code and they have just terrible variables. And you're like, I don't know what you're trying to achieve. I had someone literally last semester, all of their variables were named after animals, like Chihuahua, iguana. Like, it was not helpful. He did not do very well. But anyway, the second part of this question is, there are, I believe, 5 syntax errors. Find them. There might only be 4. Oh, wait, there we go. Error 5. Okay. I see a lot of progress being made, so I'll go ahead and start doing them. Someone want to start shouting some out? You went last. So you can give me one.
Well, mist and mist should probably be spelled.
Yes, exactly. This and that are not the same. Kaylee, give me one.
After the first standard logic, doesn't it mean a semicolon?
Exactly, yes. Yes. Go.
Law and behavioral should be the same.
Yes. Behavioral and blah need to match. Doesn't matter. So I may have ended up with blah, and that's a trap, right? Because that's okay. This does not have to be behavioral, but they do have to match. One more. Anyone got it?
We're missing an arrow by the H assigned to L, because that's.
Oh, yes. Looks like there's 6. I'll actually do that a lot. I try and do that so you guys, if you don't have to find all of them, I'll say that there are at least 5. This time it was an accident. I tried to make 5. Got carried away. Got it? It's a type error. I'll give you that hint. Yes, but that's not what I'm getting at with this question, because that's not a syntax error, right? Because this is a D latch, not a flip-flop. I misspoke when I did that. This is a D latch.
Does M need to be compared to?
Yes.
Bit 1, yeah.
or 0, right? You don't have to know if it's an active high or active low enabled, but I can't say if M. If M was a bit type, I'd be fine, but it's a standard logic. So I have to do a comparison. Anyways, you're going to get something like this with very similar types of errors. Semicolons, kind of typos, mismatch, might be like vector sizes. Yeah.
So from what you were saying, if they were bits
Yeah.
instead of standard logic, if you were to say if M, it would just assume that's a 1.
If M works, because M could, if it's a bit type, the only values that M can be are 0 or 1. So in other words, if false or true, right? If true, if M is true, so if 1, then you're good. Because this isn't a logical expression that outputs a bit, right? This is a comparison that is either true or false. But if it was a bit, if M is a bit, then it's fine. But because the issue is standard logics don't have to be 0 or 1, right? They can be X or U or Z or whatever else. Okay, let's keep moving. I got 40 minutes left. I can do this. What's next? Oh, I like this one. I'll just say it out loud unless people want me to do it. So, well, I'll draw at least part of it. Okay. I would say something like, given this counter, please draw me circuits to make it so that this counts from 3 to 6 in a cycle. Other question, anyone?
So load enable, that's basically saying load in whatever value is
Yes.
in addition to reset. Or
So they're different inputs. So this one resets to 0. Loads whatever the value is.
of course reset is just, counter entirely, right? Or,
Say that one more time.
oh, nothing, I'm just not to myself.
Okay. Right, there we go. Now, there's two ways that I could ask this as well, right? I could say, draw me the minimum circuit that does this, or I could say, draw me the circuit that does this. There's a subtle difference in that the minimum circuit is just a 2-input AND gate. Technically, that works as well, right? It's just that this will never happen, so we don't care. That's all. That's all this question is. Any questions on that one? The reset is kind of a red herring. You don't actually use it. Yeah.
Can you just explain what the load enable is doing again? Sorry.
Yeah. So load enable is just a way of saying that instead of counting, we're going to pull in these values. Yeah, there has to be some way with a load to tell it when to do that. That's all. Yes.
So for inputs, the 0, 1, 1, is that just like where we wanted to start?
Yes, exactly. So when this output gets true, where do you want to go? I want to go back to here. Also go back and review the example that I did that had the BCD counter, right, from those lecture notes, because I might ask it in that kind of context. Give me a 3-digit BCD counter. It could even be give me a 3-digit BCD counter that counts 0 to 3 in all digits or something like that, right? It's the same ideas of when do you reset, when do you load, that kind of thing. But I can also ask these kind of questions using VHDL code instead of a figure, that kind of thing. I don't think I will with the counters. If I do ask another question that I really like, nope, never mind, that one's going on the exam. I like this one. So I would ask, using only D flip-flops, design an asynchronous clock divider to get a clock 8 times slower than the input clock. If I'm feeling nice, then I would provide you with the flip-flops. Maybe the right number, maybe not the right number. Okay, so this one normally I would feel a little bit bad about because we didn't do quite a lot enough homework with this. We only had like 1 or 2 questions, but it's directly out of the notes, right? Directly out of the lecture. Kaylee, how do I do it?
First, wouldn't you need 4 if it's an 8?
Pretty sure we only need 3. We can draw a timing diagram afterwards if we want, but how do I start? How do I connect this up? Yeah, so there are a couple ways. Do you know? Does anyone know?
Well, we could start by connecting clock to D and clock on the first one.
A clock to DN clock. That would be interesting and would create a really bad race condition, actually, right? Because you have the T setup time here, which is definition 0 if you do that. But we don't need D to change on the clock, right? And so the first hint is asynchronous. Asynchronous means the clock, the fast clock, is only going to the first one. And the output clock needs to come from somewhere else. But there is a way that we can create a slower clock using just a D flip-flop. And Q then is a half-speed clock. And then I just rinse and repeat with the half-speed clock. This is clock divided by 2, that's clock divided by 4, that's clock divided by 8. Is brains melting yet? I can ask the same question with T flip-flops. I can also ask this with actually JK flip-flops. That one's harder. Probably won't do it. No promises though. Okay, next one. Well, I still got time. Oh, if I really, really wanted to be mean, right, I try not to ask too many very hard questions, but I always have one hard question. If I want a hard question on this one, I'm not going to do it, but you may want to take note because there's a good one to practice. Is using this circuit then, this would be the next part, is first make it. Part 2 is draw a timing diagram that would result from having a 5 kilohertz input clock and a 150 microsecond clock to Q delay. So all that is saying that, well, you have to assume, and I would probably say on this, like clock starts low and Q bar at time 0 is equal to 0 or something like that, right? I wouldn't have to say that. You can make the assumption. And then you would just do the timing diagram, right? You would start by drawing the timing diagram for D. And then you would do D, we'll call this D0. And then you do it for D1 and do it for D2. That's all you do. So the question was a 5 kilohertz clock with a 150 microsecond clock to Q. Now, the trick on this one, that question, is recognizing that 5 kilohertz translates to a time period of 1 divided by 5K, which is equal to 200 microseconds. So that tells you that your clock to Q delay is 3/4 of 200 micro. Right? That's what that's kind of testing that question is, that you remember this frequency to period conversion. So that when you have this clock, well, from this rising edge to that rising edge is 200 microseconds, because that's what it means to be a 5 kilohertz clock. And then, well, if I'm 3/4 of that, 150 microseconds, that means when this clock happens, I don't update until here. And then that cascades, right? Because this delays, and then it gets delayed from this rising edge of that clock, and then this one delays, right? So by the time I get to the clock by 8, my clock by 8 is delayed by 450 microseconds. Okay. This next one is easy. I kind of front loaded with the hard questions. I think that was a good idea. How much time do I have? There's a couple I need to get to. Okay, we're good. Shift register question. This one will be easy. If you're given a shift register, I'm just going to draw it this way, but I would probably draw it as a circuit, right? But we've covered that. Given a 3-bit shift register that starts out with value of 110. What is the this is a new vocabulary word. I would definitely explain it if I did it, or I would be just the way I drew it. This is called an end around barrel shifter. But really, I would just tell you something like, this is how it's connected. What is the contents of this shift register after 4 o'clock cycles? Well, it's actually pretty easy, right? It's just we shift it out and it comes out and then back around and back in. Now, I drew it this way. I could just as easily give it to you in like D flip-flops or SR flip-flops, probably D. And then just connect up the wires that way, kind of like how I showed you how to do the parallel load one. And it would just move the 0. I'm just only going to move the 0 because it's pretty easy 4 times, right? So 1, 2, 3, 4. So the 0 is here, 1's in the other spots. Right? That's all a shift register is doing. If I didn't have the end around connection, then it would just kind of dump it out and it would take whatever is in, right? Anyways. I don't know what I was thinking with that one. Okay. I'll give you a quick reminder because we didn't do any homework on it. This is the addressable memory question. And really, it's just a mux question in disguise, right? That's all addressable memory is it's going to have some contents like has an address that goes into a decoder, which is really just an unmux, right? Does everyone remember decoders? Where if I give it address 0, so this is like address 0, this is address 1. And then I just tell it if I'm going to have like blocks of memory that these access and then output. And the way those really work is if I choose address 5 gets put into this is all it's really doing, right? So if I choose address 5, it has this AND gate, so it says it asserts 5, which enables these AND gates, and then delivers to the output of this AND gate the contents of bit 50 or bit 51, right? Where they're drawn like this. So this is bit 00, this is bit 01, 02. This is bit 10, bit 11, etc. Right? Does everyone get that notation? And so then I get access to that out here is my registers. So I could ask a question, like I could draw up a grid array like this and give it values and then just tell you, if I give you an address of X, what is my output P? Right? It's not going to be much more difficult than that. I could extend it and ask you specifically, what is my bit if I give an address of here and then an address of this parallel output, right? Because if this is P, then I could ask you, what is P at 4 for address 2 or something, right? Something like that.
Right, that's going to be the, well, technically the fifth.
Yeah, the fifth of whatever this is. So understanding this type of structure, as well as how an address works, those are the two concepts you have to take away from the addressable memory. There will be a question about that on it. If you're unsure how addressable memory works, so it's not in the book. This is just something that we have in the class requirements. It's not really addressed very well in the book. Email me and we can talk over Zoom or whatever, and I can kind of walk through it. But it's not supposed to be a hard question. It's just supposed to be something I have to cover. Memory is kind of important anyways. Okay, another question. I'm running out of time, so I'll make sure I get this out. Just a few of the other example ones is I could ask a nice easy one. Design me a 16-to-1 box using only 4-to-1 boxes. Everyone think they could do that? Everybody did that. Other VHDL type questions I could have, this is the last thing that I have on my list, is I may do like more type error type questions, kind of like what I did up with this earlier code where there was a type mismatch. Another one that I could do is using assert statements. I may say declare like one signal that's an unsigned, declare like a constant that's an unsigned, a signal that's a standard logic vector, and then somewhere in the code it would say assert standard logic vector equals unsigned, right? It wouldn't say that because they'd have variable names, and that would be a type of error, right? Where you can't compare two different types of numbers. I could, and this one is just kind of hard to prepare for, hard to study for. This is mostly for making sure you've done the work in lab, is I could provide an error message that Vivado gives me. So like write up some code, make an error message, and then just give you the error message and ask you, like give you the code, the error message, and say, what's wrong? What are you wrong in this code, right? Making sure that you can read Vivado error messages, which they'll be the kind of thing that you've almost certainly ran into in the process of debugging your code. Make sure you know how to write for loops and generate loops. So I have to think about this one a little bit. One thing that not everyone knows, I've kind of talked about it individually with a lot of people. If I have an ampersand, that's a concatenation sign. So like if I have a signal A that is equal to 0, 1, and B that is equal to 1, 0, and I do C equals A and B, then C is equal to 0, 1, 1, 0. That's all concatenate means. Just take two things and mush it together. That might show up on the exam for one question that I have notated. It's just important to know that. I may also include like the hint kind of thing. Okay. When I ask you to write code, I will almost certainly ask you to write some handwritten code in this exam. When you do, you're perfectly welcome to shorthand it. 4 down to 0, for example, like the down arrow, like I do. I'm not, unless I specify, I'm not looking for perfect syntax. I'm looking for concepts. So I'm not going to fault you for getting things like begins or semicolons or that kind of thing. But so 4 down to arrow is fine. But if your like vector size isn't declared or is inaccurate, then I will mark that down, right? Things that are conceptually important. Semicolons at the end, not important. Begins, not really that important. But making sure that size matches is fine. Type matches are important, right? That kind of thing. Functionality is what I'm testing for in handwritten code. I could take something, I'm really thinking about this one, how to do it well, so it's clear to you guys and doesn't like end up as a trap. But one way is give you guys code and ask you to draw me the block diagram. So it'd be code that is kind of similar to the project one that you've done. And I would ask you, here's code that's similar to project one, draw me its block diagram. And that would just be a matter of looking through the code and finding what connections go where, drawing some modules with inputs and outputs, and then drawing their connections, and then drawing the top level with its ports, right? That same kind of block diagram that I draw on the board constantly in lab. That's probably the way I end up asking that question. I could also draw the block diagram and provide the code and just ask, do these match? Like, does my code do what this block diagram is supposed to do? All right. That is all of the questions that I have. Do you guys have any questions? Yes.
So it's still going to be open note.
Open note, open book, open internet. Yeah, organize your notes well is one of my strongest suggestions because I will be pulling questions that are straight from the notes almost certainly. It's kind of just inevitable. Have your homeworks handy. Like a lot of the ones that are going to look like tricky questions are just going to be homework questions or very similar. That's just kind of testing to make sure you've done the homework, right? I'm going to try not to kill you guys with the exam, but we'll see. This is a new kind of exam format for me because the content's a little bit different than it has been in the past for this stretch of things. Yeah.
So the only type of delay is like a clock to queue and a gate delay, right?
That's the only thing we're worried about, yes. There are other kinds of delays outside of the scope for now, so I won't cram any more of that into your head. Be aware of concepts, right? Because I don't think I'm going to test like setup or hold time requirements, but be aware that they exist because like what we ran into earlier, one of these examples would have been kind of apparent that it was a problem if you remembered it, right? So be aware of their existence. I don't think I'm going to ask about them. I'm going to try and stick to the types of questions we covered here on the exam. I don't like to surprise students. One of them will be more difficult than the examples that I've done. Everything else will be as or less. So there's going to be one hard question usually, and then a bunch of let's like make sure you know what you're doing kind of questions. There will almost certainly, I don't know if I mentioned this, be questions. I did actually, like the VHDL. What is this VHDL code doing? What device is this VHDL code? Right, where the answer was D flip-flop. And the answers could be MUX or decoder, encoder, right? Any of these kind of like key phrases that we've mentioned that are specific types of devices. I'm not going to bring up a new device that you haven't worked with or at least heard about in notes, but I will test on at least some subset of the ones we've talked about. MUXes, encoders, decoders, BCD converters. If it's anything more than here's a BCD block, do it. That's going to be like one of the harder questions, so everything else is easier. I expect there to be, I don't know, 4 to 8, just kind of either multiple choice or short answer, just concept questions.
How many questions are you expecting overall?
I think those 4 to 8 plus 6 to 8. I think. I can count actually how many. I think things change sometimes, but yeah, 6 to 8. I counted 7 that I want to ask. That list I kind of went over at the beginning is more or less the questions I will ask at the very beginning. Okay, I'm going to end this recording then, and we can all go fall asleep. You've got until next Monday to prepare, right? Monday night.